As we observed in the example of join optimization, the cost-based optimization is expensive, even using dynamic programming. So, the database management systems, while implementing cost-based optimization, may also bring in heuristics to reduce the number of plan choices in their cost-based optimization. Heuristic plans offer a good starting point or transform the query expression by using a set of rules that usually improve the execution performance. Note that these rules are heuristics and may not always end up actually improving the execution performance, but they typically do. While the number of systems that only use heuristics is limited, many systems actually combine heuristics with cost-based optimization for limiting the search domain. Let's take a look at some of those popular heuristic rules. For logical plans, this could include rules like perform selections early. This, if you remember, was introduced using push laws. The reasoning behind this rule is the fact that it reduces the number of tuples as early as possible during the evaluation. Another one we have seen before is perform projections early. This also reduces the number of attributes. And although it is less effective than reducing the number of tuples involved, it still helps in reducing the size of intermediate results. Another one is perform most restrictive selections earlier, which intuitively is trying to limit the size before other operations which grow the size are introduced to the intermediate results. On physical plans, these rules can look like defining preferred access paths. For example, if logical plan calls for a selection with one condition like attribute equal constant on a stored relation R, and relation R has an index on that attribute, we can perform an index scan to obtain only the tuples with attribute equal to the value. This is an attempt to reduce the cost using the access plan that uses indexes. Another one is if an argument of a join has an index on the join attributes, use an index join with that relation in the inner loop. Or preferring a sort join to a hash join if a sorted output is required, and ultimately a sort operation needed. Now, let's go back a little to the discussion about nested subqueries. How do we handle them? Do you remember the nested query parsing and array tree generation in our query processing part 1 discussions? As we saw there, repeated in this slide here, one main way of dealing with the nested queries is transforming the nested subqueries to joins where possible. In this way, the nested query is eliminated early on, and the optimization can be applied on the whole query as a single query block. However, there are limitations to this approach. Generally, the inner queries are like functions that take parameters and return a single value or set of values to the outer query. But evaluating a nested subquery by invoking it as a function is not very efficient. That is why we replace the evaluation of these functions by an equivalent expression without the nested loop, as we saw before. This can happen if there is no correlation among the inner and the outer subqueries. Nested subqueries, however, may include correlated subqueries. Correlated subqueries are subqueries that have variables from outer level query. These variables are called correlation variables. For example, the query here include e.stid from the outer query in the subquery. If there is a correlation, we can break it through a complex process called decorrelation. Decorrelation is the process of replacing a nested query with a correlation with a query containing joins. In this case, the query can be evaluated by computing the Cartesian product of the relations in the outer from clause and then testing the predicates in the where clause for each tuple in the product. However, when correlated variables are involved, this process is a lot more complex. And in some cases of complex queries, including aggregates and nested subqueries returning tables, may not even be possible. In these cases, unfortunately, the typical strategy is to evaluate the nested subquery for each tuple of the outer subquery. This is called correlated evaluation.